Let's take a look at question number 3 from worksheet number 4 from your homework last night. It says a 4-kilogram ball traveling north with a momentum of 11.2. This throws us off a little bit sometimes because usually we're given its velocity instead of its momentum. It's not a big deal though. If you're more comfortable dealing with velocity, then get the velocity. Just divide momentum over the mass to get the velocity. A little bit of a shortcut maybe though if you go with the givens that we have there. Collides with a 6-kilogram ball traveling west with a momentum of 18. They stick together and head off as one. What's the momentum of the combined mass? What's the velocity? And then I asked you yesterday to determine whether they were elastic or inelastic as well. All right, so here's the situation. Object number 1, 4 kilograms. It's got a momentum of 11.2 kilograms meters per second, not a velocity. Don't get that mixed up, okay? It's a momentum. We have object number 2 going to the west with a mass of 6.0 kilograms and a momentum of 18 kilograms meters per second. After the collision, they go off as one. They're going to go off north and west somewhere up in that direction. Doesn't matter if we're perfect with that. We got to break this up into x's and y's first. There's no funny angles to deal with here, so we don't need to do any little aside to figure out how to get rid of that 32.5 degrees or whatever the funny angle is. It's all straightforward in terms of angles here. Here's our x's. The pi is equal to pf. m1 v1i plus m2 v2i equals mvf, combined mass because they've stuck together. M1 is 4 kilograms. We don't know what V1I is, though, do we? We don't need to know what V1I is. This entire momentum is 0. How come? Because Connor's kind of putting his finger up in the air like this, because it's going straight up, right? We're dealing with the x component, and it's going straight up in the y direction. So we'll get rid of that. Now, M2 is 6 kilograms. We also don't know what V2I is, but we don't need to know that one, not because it's 0, but because we already know that the total momentum m times v combined is already 18, or negative 18 because it's to the left. The combined mass here is going to be 10 kilograms, but you know what? Why don't we just find the final momentum instead of the final velocity, since that's part of the question anyways. So PF in the x direction is 18 kilograms meters per second to the west. In the y direction, we're going to say, again, PI equals PF. This time, M1 V1I is 11.2. We don't need to multiply a mass by it because we already know its momentum. This one is 0 because it's horizontal, not vertical. And the combined momentum is, again, what we can find there. We can do our Pythagorean Theorem thing, but we first have to draw a vector diagram. We've got 18 to the left, and we've got 11.2 up. The final momentum is equal to 11.2 squared plus 18 squared, square root it. And when we do that, we end up getting 21.2. The angle right there is the inverse tan function of 11.2 over 18, and that gives us 31.9. This is going to be north of west. Want to find the velocity? You can just say V is equal to P over M. It's 21.2 over 10, the total mass, or 2.12 meters per second. We've done the first part of the question. Is that okay? Does that make sense to people right now? thus far. Let's do the kinetic energy part of it. We know the EKI is equal to 1/2 m1 v1I squared plus 1/2 m2 v2I squared. Now, there is two dimensions to this. There's an x and a y. Object number 1 is going one way. Object number 2 is going another way. But that doesn't matter anymore. It did for momentum, because momentum is a vector. We had to break it into components because of that. But kinetic energy is a scalar. We need to leave it. We need to treat this object number 1 the same as we treat object number 2. It doesn't matter that it's going perpendicular to it. 1/2 of mass 1 is 4 kilograms. We also need V1I, which we do not have. We're going to solve for V using momentum over the mass. 11.2 over 4. What does that equal? 11.2 over 4. 2.8? 2.8 squared plus 1/2 of m2, which is 6 kilograms, times V2I, which is 18 over 6, or 3 meters per second. Solve for that kinetic energy. What does it work out to be? 42.68, 42.7. Anybody else get that? Yep, good. All right, so let's get EKF now. We're predicting that it's going to be less, right? But let's just make sure. This one's easier because it's just 1/2 mvf squared. The combined mass is 10 kilograms, which is also an easier number to deal with. VF was, what was VF? 2.12. So now we're going to say 0.5 times 10 times 2.12 squared gives me 22.5. So besides the fact that they stick together, what is it that tells me in this question that we have an inelastic collision? 4 words. Kinetic energy is lost. Okay, when we lose kinetic energy, we have an inelastic collision, which is what it's going to be most times. Right? You ever get a question that's multiple choice, and you're strapped for time, and you just don't have time to figure it out, and you've got to guess? Guess inelastic, because most times it will be. Okay, the exceptions to that might be if it's, well, if it's subatomic particles, could be elastic. Okay, or even something like billiard balls, hard things that don't want to compress, that don't want to squish. Okay, they could be, to the right number of sig figs, elastic as well. But most things, anything that squishes at all, is going to be inelastic. So it's usually it's about 90-10, your chances of guessing correct on those questions, or maybe 80-20, your chance of guessing correct if you have to guess whether it's elastic or inelastic. Okay. All right. Are those other two questions okay? Having gone over this one, are they good? All right, what I'd like to do right now is write out on the board here just a very, very quick outline of what we've done this unit, and just remind you about a couple of little things. We talk about a strategy for preparing for this test. Okay, the vast majority of preparation for this test you've already done. So that should feel good. That should feel good that you don't have to go home this weekend and work for 16 hours preparing for this test. If you've done your work, and if you've kept up with things, and if you've understood things, then you should be in pretty good shape for the test. In fact, you should be able to come in without even studying and do okay. You don't want to do okay, you want to do well. I'm saying that the biggest part of preparation is what we do on a daily basis. As long as you keep up with it, and as long as it makes sense. But what should we do this weekend? Well, the first thing you should do is actually study. Read through things. Read through your notes. Read through your notes for those little things. There's little things that you don't always see when you pick questions to do. You can't do every question that we've done this unit. You can't do every question in your worksheet book, every multiple choice question that you have available to you. You don't have time to do all of that stuff. So you're going to have to pick questions. You want to read through all your stuff just in case none of the questions that you've picked involves some little thing. So you want to remember that little thing by studying it, even if you're not doing a question this weekend that involves that little thing. Read through, then practice questions. And if you're good with those practice questions, and things made sense to you when you read through it, you're probably going to be just fine on the test. All right, so what is this going to look like? Well, the first thing we did was just the general concept of momentum. We defined it. We talked about the units, the vector nature of it, so on and so on and so on. Momentum. Excuse me. We didn't talk about momentum. That's for another day. Momentum is what's on Monday's test. Okay. Momentum, if you're curious about what that is, then I would suggest you go home and you look that up. Okay. And if you can't find anywhere on Google that it has momentum, then you should look harder. Go to the library. Go to the bookstore. Okay. Spend hours trying to find the word momentum and what it means. Okay. And then let me know on Monday what it means. Okay. What else did we do along with momentum besides the basic calculations, the equation, the definition, and so on? We also did that little thing, excuse me, variable value changing. Remember what that was? We had a momentum of 10, and we tripled the velocity, and we quadrupled the mass or something like that. We wanted to find out what the new momentum was. And we can do that with momentum. We can do that with any equation. With impulse, with equations that you learn in the next unit and the next unit after that. Okay, I write it with this because that's when we did it, was with momentum. 2, impulse. You need to know the qualitative implications of impulse and the quantitative nature of impulse. By qualitative, we mean those two general things that can be explained by impulse. The first one being that situation where you have a predetermined impulse, an impulse that is going to be the same no matter what. That occurs when the object is stopping. A car crashes. A car comes to a gradual stop at a stop sign. The impulse is predetermined. It's going to be the same in both situations. You jump off a desk. Your impulse is going to be the same whether you bend your legs or not. You catch a baseball. The impulse of that baseball is going to be the same whether you catch it with your bare hands or whether you catch it with a baseball glove. It doesn't matter how it stops. The impulse is predetermined. The idea there is that we usually try to maximize the stopping time which minimizes the force. Now, the converse of that could be exactly the opposite, right? There's the odd time when perhaps you may want to actually minimize the stopping time. What effect would that have? It would what? It would increase the force, right? So most times you don't want to increase the force, but there may be that odd situation where you're trying to maximize the force as opposed to trying to minimize it. Vast majority of the time it would be this way though. Now the other qualitative implication of impulse is when we don't have a predetermined impulse, when we affect the amount of impulse that an object experiences. That occurs when you're trying to start an object. A golf ball sitting on a tee. Okay, a car sitting at the stop sign. When you're trying to start the object, generally what you want to do is maximize the impulse. when you maximize the impulse, you do it in one of two ways. You can increase the stopping or the time of contact, or you can increase the force. Both of those will increase the impulse. So the first one, increasing the time, decreases the force. And the second one, it doesn't. The second one, increasing the time, increases the impulse as well. Then, of course, the quantitative nature of impulse, just the equation, basically, and be able to deal with that. Delta P is equal to F times T, and that's equal to M times delta V. Okay? Be alert for those little things like VI is equal to 0, even if it doesn't say that. Read between the lines. VI is equal to 0, or VF is equal to 0, or whatever. Make sure you're in the right units. Okay, there's been a couple times, once or twice, when we've been able to use whatever units we want, if we've chosen to do that. Here you can't. Units don't cancel out of these, so you can't ever, for impulse, use, for instance, kilometers per hour. 3. Next, we did conservation of momentum in 2D, 2 dimensions. In 1 dimension. That was next. So that was PI is equal to PF. Remember, when the law of conservation of momentum is valid, we're allowed to use it whenever we have an isolated system. You guys remember what an isolated system is? You got no outside forces acting, right? No external forces acting. You can have internal forces. Okay? A truck, a semi-truck, hits another semi-truck. There could be 2 people in the back of one of the semi-trucks wrestling. I don't know why I picked that example. It seems like a silly example. But there could be. There could be 2 people in the back of one of the semi-trucks wrestling, and 2 people in the back of the other semi-truck playing catch with a baseball. The internal forces there don't matter. The force of one wrestler on the other doesn't matter. The force of the guy on the baseball or the baseball on the other guy's hand when he's catching it doesn't matter. Those are inside the collision. Those forces don't matter. Okay, we're allowed to have those. We're not allowed to have external forces like a big wind that pushes one of the semi-trucks. Okay, because that takes energy away from the system, or takes momentum away from the system, or adds momentum to the system. So internal forces are good, external forces are bad. Be able to solve conservation of momentum problems using PI equals PF in 1 dimension. Then we did elastic and inelastic collisions. Just remember that an elastic collision is when kinetic energy stays the same. Inelastic is when kinetic energy is lost. Now, if 2 objects hit each other and they stick together, it's going to be inelastic. If they bounce apart, it could be either one, elastic or inelastic. You need to be able to determine mathematically whether it's elastic or inelastic by calculating the initial kinetic energy, and then separately from that, the final kinetic energy, and then comparing them. Now, one thing you got to remember here is that direction doesn't matter, because kinetic energy is a scalar. So if you've got one that's to the north, one that's to the south, let's say one guy's going 4 meters per second to the north, the other one's going 3 meters per second to the south. So 4 and -3. When we plug them into momentum, it'll be 4 and -3. Plug them into kinetic energy, it's going to be 4 and 3. We drop the signs, we drop any indication of direction, because we're talking about kinetic energy, which is a scalar. And next we talked about 2-dimensional collisions, or conservation of momentum. In 2 dimensions. Remember the x and y components. Remember the I don't like funny angles. Remember if you're asked for velocity, you also need direction. If you're asked for speed, you need only the magnitude. Remember that the angle can be found by the inverse tan function. Let's keep straight the opposite and adjacent. Okay, let's remember when we're calculating the magnitude that we're using the Pythagorean Theorem, and we don't forget to square root it. Okay? Little things like that, right? Odds are, if you go all the way through one of these problems and you forget to square root the value to get the final speed, odds are that a number that you get will be an option. If you forget to square root, that number will probably be an option. So be careful with things like that. Okay, check to see if it's reasonable. Little things like that are what's going to guide us to doing well on this test versus doing okay on this test. And then, of course, with conservation of momentum in 2 dimensions, we also did elastic and inelastic collisions. I'm not going to write that down again because it's the same thing, right, as number 4. Just remember that with conservation of momentum, we do 2 dimensions. We do vector components, x's and y's. With elastic and inelastic, we don't. One truck is going to the north at 20 meters per second. One truck is going to the west at 12 meters per second. For momentum, there's an x and there's a y. For kinetic energy, there's a 20 and there's a 12. Doesn't matter which direction they are. All right, that's pretty much it. You look at that and think, geez, there's not really very much, is there? And we go back to it and we say, like, you know, we took, you know, 2.5 weeks or so here, 3 weeks basically to do this, or 3 and a bit actually, to do this. But it doesn't seem like all that much. You know why? Because you for the most part, you get it now. That's why. It seems not so bad, like not so much, because we understand it. As we're going through it, it seemed like quite a bit. Okay, you go back and study this weekend, check these off. Okay, do some problems in this, do some problems in this, do some problems in this. And then as you feel like you've mastered something, check it off. Be aware of some of the other little things too, though, guys, that just apply to everything, like units. Okay, circle your givens when you see your test. Circle your givens. Draw attention to anything that can lead to silly mistakes, whether it's a unit or whether it's a direction, a north-south thing, or whatever. Okay, circle crazy things. Bring in a package of, you know, rainbow highlighters so you can have a color-coded system. I don't care exactly what you do, but you need to recognize those tiny little things, right? Okay, show work. Even though it's multiple choice, you're not going to get marked on work. Show some work, because that helps you. If you need to find something, that helps you to avoid making a mistake. Forget whether it was this class or my last class that I mentioned this to you yesterday. When I do an answer key for a test, sometimes I get lazy, and sometimes I go through it and I don't show very much work because I'm doing the answer key. Now, most times I do that. I still get the question correct, most times. But every once in a while, we have an answer key where someone says, Mr. Dickie, I don't think that's the answer. I think it's whatever. Sure enough, I've made a mistake. Every once in a while, that'll happen. Almost all the time that happens, almost every time that happens, it's because I didn't show any work. Because I just, you know, I started putting numbers into calculators and I thought, oh, I'm good at this. I can do it without showing work. And then I ended up making a stupid mistake. It doesn't happen often, and it might not happen often with you, but we don't want to take that chance, right? So show some work, okay? You have more chance of getting it right. Okay, details like that, or get us from a, you know, say a 65 to an 80, or an 80 to a 90, or something like that. Okay, what's the format of the test? There is 18 questions, 14 multiple choice, and 4 numerical response. And if it makes you feel good, question number 1 is easy. I won't comment on the other 17. There's varying questions, right? There's lots of easy ones, and there's some challenging ones. Any questions? Corey?